Now, so having done all of this, we want to do something parallel for gravity and see where it leads us. So that is going to be the strategy. And for this, we simply start with the equation appropriate for gravity and follow the same procedures. So this was electrostatics. This was the Poisson equation of electrostatics. And as you know, in Newtonian gravity, there is also a Poisson equation. Which is like this, and there's really only one big difference between the two sides. Okay, of course, the constants are fixed by experiment, so nobody says GE has to be the same as Gn, but the conceptual difference is that while rho E is a charge density, rho G is a mass density. That's the huge difference. And it's responsible for everything. So these are all experimentally well-known facts. Just as electricity comes from charges, charges are the source which cause electricity to happen. Similarly, masses are the source which cause gravitation to happen. Gravitation is the effect of mass. Now, the first step in making this relativistic is to ask what are the transformations of rho g under Lorentz. So how does it transform under Lorentz transformations? And here we find a different answer from the left side. This quantity is mass upon free volume. Okay. Now earlier, when it was charge upon free volume on that side, we argued that since 4 volume is invariant, we can think of this as the zero component of a vector. But now, mass is here, and mass in relativity is promoted to energy, and that's also the zero component of a vector. So this roughly becomes energy over 4 volume into time. And you see that time is the zero component of a 4 vector, time x1, x2, x3. And energy is the zero component of a 4 vector, energy, momentum p1, p2, p3. Okay, both are zero components of 4 vectors. And therefore, since I'll write it, since energy and time are both zero components of 4 vectors, rho g must be the 0, 0 component of a second-rank tensor. In special relativity, a tensor is just something which transforms like a product of many vectors. Each vector has a linear transformation under Lorentz transformations. If you multiply many vectors, you get something with many indices that transforms in a certain way. Then a tensor is anything which transforms in the same way. It's very easy to understand tensors. Okay? And that means that the right side of this equation should be written as 4 pi g Newton. Then we have to give a name to this tensor. I'll call it capital T and put 2 indices 0 here. So this is going to be the right side of the equation, of that equation. But of course, if some component of a tensor appears in an equation, then all components of that tensor must appear in the equation because of special relativity. So I'll just write the whole tensor in union. We'll see in a moment what is the physical meaning of King union. Now this fact tells us that on the left side we must also have a second rank tensor. That grad squared again turns into the D'Alembert or box, which is minus d by dt squared plus grad squared. Okay, that's the correct special relativistic generalization of that thing. And here I must put some variable which is a second rank tensor whose 0, 0 component is phi. Now for purely conventional reasons, I am going to call that minus h bar mu nu upon 4. Okay. What I call it, you can't argue with whether I call it h or h with a bar. There's a reason for the bar. As for the minus 1 by 4, it's just normalization between some notation I'm going to use and the notation of phi. So you can't argue with that either. Just a convention. So I'm going to set these to equal. And this is going to be my equation, analogous to the equation on this side, which I didn't write down today. Box of A mu equals 4 pi g times j. It's analogous to that. Okay. Now we had an easy time on this side guessing what was the 4 vector whose 0 component is the charge density. That 4 vector was the current. Now we need to ask what is the second rank tensor whose 0, 0 component is the mass density. And there is such a tensor in all physical theories, and it's called the stress energy or the energy momentum tensor. And this tensor plays a similar role with respect to mass as the current plays with respect to charge. Okay, the 0, 0 component has to do with mass density, but the other components all have some physical interpretation, and it includes quantities which are sort of scalar as well as quantities which are associated with movement. Just like a current has a part rho which is just the density, and then a 3 vector current which is something to do with moving charges. This has many components. It's really a 3 by 3 symmetric tensor, so it has 6 independent components, and all of them have some physical interpretation, and we'll encounter that physical interpretation as we go along. Now, one of the most important things about this, so first I should say that a property of this, which is analogous to J0 being
sir,
yes.
How from here we can call it symmetric?
Symmetric. Okay, we can't actually from here, you're right. Okay, one thing we could do is that we could decompose this equation into its symmetric and antisymmetric part. And if we don't need the antisymmetric part, then we'll throw it away. We'll just say there is nothing on the right side nor anything on the left side to take care of the antisymmetric part. Okay, in general we always like to keep things as economical as possible. Okay, we'll certainly need the symmetric part. In any case, the energy momentum tensor as defined independently is symmetric, so it all sort of fits. And anyway, I want to emphasize again, it's not a derivation, it's a heuristic kind of thing, yes.
So is this a theorem that if some components of a tensor appear in some equation, then all components of the tensor should appear?
Yeah, if it's a relativistic equation, then obviously it's a theorem. You cannot have a relativistic equation in which some components of an object appear and others don't appear. The equation must be made up. What are the variables in the equation? There must be scalars, in which case there is only one component, or vectors or tensors. But say it's a vector. Let's say there is a vector in nature. I can't have one component of it in my equation and other components not being there. And one of the easiest ways to think of that is forget about relativity, think about rotational invariance. Okay? If your system has got rotational invariance, then you can't say that from now on I am going to only discuss velocities in the z direction, but there is no place in my theory for velocities in the x and y direction, because after a rotation, you can make your velocity which is in the z direction point in any direction you like, in fact in any combination of x, y and z directions. Okay? Therefore the equation has to have the whole 3 velocity and not just one component. Good. Now, so one property of the key property of T mu nu, as I said, we'll be going into lots of examples of T mu nu which will make it clearer to you later on. But the key property is that T mu 0 is P mu, is the form momentum. Or perhaps the correct thing to say is that integral of T mu 0 over over space is the form momentum. So yeah, if I didn't integrate, then it's the form momentum density. Let's keep it like that. This is the form momentum density, form momentum per unit volume. So if I integrate this over all of space, then I actually get the form momentum. Alright, this shows you that if mu is 0, then T00 is the 0 component of the form momentum density, which is the energy density, which is exactly what we started with. So everything is right so far. Yes.
From there,
Yes.
when we want to generalize rho g, we can say that one way to generalize it is rho into the product of four velocities, and from there we can see it is symmetric.
Rho into the product of four velocities.
Like rho into mu, u mu.
2 for velocities.
Yeah.
That's correct. You can do that.
And
That's the way it's normally done in books.
Yeah.
But normally in books, people are going in the other direction.
Yeah.
Okay, they already know it's symmetric, and then they take the 0, 0 component. They take a particular P mu to be rho, u mu u. You're correct. Okay. Now the important property of this energy momentum tensor that's useful for us is that exactly like the current we discussed on the left side, this also is conserved, which means that it satisfies d mu, T mu equals 0. Here it has two indices, so you can take the divergence with respect to either one of them, but it, of course, by symmetry, it doesn't matter. So this is the conservation of energy momentum tensor, and the reason we believe in this is that through this relation, that tells you that the form momentum doesn't change in time. Okay, so that's conservation of energy and conservation of momentum, and these are very, very important experimental facts about life. So you can't have those things conserved unless you have this divergence list, which is also called conserved. That these are conserved in time, the integral of these components, and that follows from the fact that this is divergence-free. And that's very similar to saying that the current here J mu satisfies del mu, J mu is 0, and therefore the charge density, rather the total charge, is constant in time. Okay? So this is the conservation. I'm not going to give any formal derivation now. But we see that as before, this gives us a slight problem because this implies that del mu of h bar mu nu should be 0, which is like a constraint. And this constraint is inconvenient. We can work with it, but it's not nice to work with a very dynamical variable which is always supposed to be constrained. Okay? And just as we found a way out of that problem here, we will find a way out of the problem in the same way over here. And the method will be take the equation box of h bar mu nu. So I am multiplying throughout by -4, so it's minus 16 pi g Newton T mu nu, and add to the left hand side some combinations of the divergence of h bar mu nu to make the left hand side automatically divergence free. If you followed how we did this for gauge theories, it's exactly the same procedure, but the only complication is we have two indices, so there are many things we can do. So we can try many things, only one of them will work. I hope the strategy is clear. Since this is anyway 0, we can add it on the left side of the equation at no cost. Okay, so we'll do it, but we have to respect the fact that it always must come with a total of two derivatives at 1h, because dimensionally this term has two derivatives on h. So all the terms must have two derivatives on h. Also all the terms must have two free indices mu and mu, otherwise we can't add them. So let's try. So the possible terms are eta mu nu del alpha del alpha. Sorry. Okay. This has two derivatives and it has three indices mu and nu. It's linear in H and it's proportional to the vanishing object del beta of H alpha beta. It includes that. So it does vanish by virtue of this constraint. It should have a bar. So such a term is allowed to be added. Okay, but there are a couple more terms that are allowed to be added, and they are, for example, del alpha del mu H alpha mu. This is also allowed. This also has two derivatives. It has two free indices mu and nu, and this part, this derivative on that is the divergence, which is 0. And there's one more term which is just obtained by interchanging mu and nu. So these are the three terms I'm allowed to add. Okay. Now out of them, these two terms have to be added with the same coefficient, because only then the answer will be symmetric in interchange of mu and nu. I'm not going to violate that. This term can be added with any coefficient. Okay. So I'm going to, you can check for yourself, but I'm just going to tell you what is the answer. So if I add this with coefficient +1 and these with coefficient -1 each, I get the equation box of H bar mu nu plus eta mu nu minus and the result is the same as before. Okay. So you can't argue with this because I've only added things that are already supposed to be 0. But I want you to notice that now the left side has been cleverly put together such that del mu of the left side is identically 0. You take del mu on the left side, you'll get lots of terms. Okay, then you have to put them together and you'll find that you get 0. It's a simple exercise. And since it's 0, there's no longer any need to insist that H bar is divergence-less. You can lift that, okay, because this equation makes perfect sense for all H bar. However, you encountered a new invariance of the left side, which is responsible for this miracle, and the new invariance looks like this. The variation under a variation of H bar mu nu, which is equal to del mu of psi nu plus del mu of psi nu minus eta mu nu So if you perform this change in H bar like this, it's very similar to a gauge transformation on A mu which we saw earlier, but there's a difference, which is that A mu has one index and the right side there was this function lambda. A mu shifts to A mu plus del mu lambda. Lambda was a scalar. Here the variable has two indices and its transformation is given as a derivative on a parameter, arbitrary parameter with one index. So psi is simply an arbitrary vector. So what's the statement of the invariance? If I perform this shift on H inside this complicated expression having 4 terms, I get no net change. Okay. I could spend the time to work it out for you, but as long as you agree that it's doable, then I'll leave you to do it. If there's any mystery in your mind, then I'll try to clarify it. Okay? There's nothing but plugging in this into that and seeing that you get 0. Okay? This has 3 terms. That means each of these 4 terms will generate 3 terms, so you have 12 terms. You add up all the 12 terms and they'll add up to 0. Okay. So we've got somewhere, but we don't quite understand where we should go from here. We've got some equation which correctly generalizes Newton's law of gravitation, and it is special relativistic invariant. Okay, that's very clear from its structure. It depends only on indices which take 4 values, and the whole thing is Lorentz invariant. It will always be, as long as all your indices either match on the left and right side, or they are contracted away. In both cases, if you take care of these two things, then the equation is relativistically invariant. Okay. But neither the equation looks very illuminating, unlike Maxwell equation, which was already known. This is in some sense a new equation. I don't expect you to have seen it before. Nor this gauge transformation law, or whatever you want to call it, new invariance law, is very illuminating. It just says that h bar changes by 3 terms. So what? Okay, so where do we go next from? Now, next step will be to make use of, by the way, in my notes, these two things are proved. The fact that this has the gauge invariance I wrote, and the fact that divergence of that thing is 0 are described in my note. Yes, there's a question.
So can each bar mu be interpreted physically?
We are trying to do that. That's exactly where we are. We are trying to interpret physically.
Because in that first equation, when you made it generalized tensor equation, you wrote T mu.
Yes. So we are going to, we'll be there in 5 minutes. Just for, hang on. So we are looking for exactly what you said. We are looking for the physical interpretation of h bar mu. Okay. Many of you know the answer because you opened the book. Okay. But we are not trying to find it by opening a book. Well, I found it by opening a book. But we are trying to derive it for you over here. Okay. Derive in some heuristic way where you'll appreciate that we didn't really have many choices. We couldn't have really chosen any other law to start with except Newton's gravity because we want to study gravity. We tried to make it Lorentz invariant because we have to. We were forced to the fact that rho is the 0,0 component by its Lorentz transformation properties, which in turn come from its basic definition. And we followed everything and we got to this equation. We said this equation is fine, but it's not nice enough because it involves a constraint field. We lifted the constraint by guessing 3 terms to add on the left side, which are actually 0 under the constraint. But after we add them, then the left-hand side becomes divergence-less. So we don't need the constraint anymore. And now instead of that, we've got a gauge invariance of some kind. Okay, depending on one free vector. Okay. So now we'll make a little change of variables, which is going to help us decipher this gauge invariance. And for that, I have to go back somewhere to the top. Yes.
The way we started, like right at the very beginning, when we started, we found out that rho g had the time component to be energy. After that, we argued that okay,
Rho g had the time component. No,
it was
I mean
E into t. That's why
yeah.
it was one component of a tensor rank 2.
That's it.
So then we said that okay, we expect this to be the 0,0 component of some tensor.
Correct.
So, are there any other tensors which have the 0,0 component? As
So actually no, in fact, because in relativity one can derive rigorously and precisely, though I am not doing it just yet, that the energy momentum tensor is a conserved tensor for all systems, okay, which are systems which are appropriately time and space independent. So where energy and momentum is conserved, the energy momentum tensor is conserved. Not only that, its 0,0 component is known to be the mass density. Okay, so if you are not familiar with that result, then maybe I better do it next time. I assume people knew that, right? Okay, that's taught in special relativity. So my point was that we'll assume anything that we already know to be true from special relativity. But if you want, I can certainly explain that another time. Okay, good. So what I'll do now is to make a small change of variables. Looks very harmless, but it helps quite a lot. So let me remind you that the mysterious, so we are going to focus on this mysterious invariance delta of h bar alpha beta equals this. Or maybe I don't, but it doesn't really matter. Okay. So let's define a new variable h mu nu to be h bar mu nu minus a half eta mu nu h, well, eta alpha beta h alpha beta. What is this? Eta is of course the usual Minkowski metric. Eta alpha beta h alpha beta is the trace of h itself in h bar on the right side, taken with respect to the Minkowski. So what I am doing is taking this matrix and subtracting from it something proportional to the tensor eta times the trace of the original. Just a change of variables. That too, it's a linear change of variables. Remarkably, it has the property that the reverse change of variables is the same. H bar mu nu is also equal to h mu nu minus a half eta mu nu eta alpha beta h alpha beta. So it's a both ways change of variables. Exactly looks the same. That has to do with being in 4 dimensions. Okay, you can actually take the trace of this equation and you'll find a simple relation between the trace of h and the trace of h bar. You want me to show it to you? Taking the trace of this equation, you find that eta mu nu h mu nu, which is the trace of h. This gives me the trace of h bar minus twice the same thing, because the trace of this is 4. Eta mu nu is 4. So you get that this is minus. This is the relation between the traces of these two objects. One is minus the trace of the other. Okay. So here is the change of variables. Now, what is the variation of h mu nu? We can, of course, once I make this change of variables, I can plug it into all those equations and I'll get some equations. The equations will change after I change my variables. I'm not so interested in the equation, I'm more interested in the invariance, this one. I want to simplify it, and I claim that this change of variables does simplify it. So let's see how that happens. Delta h from this relation is delta of h bar minus a half eta mu nu eta alpha beta delta h bar alpha beta. Now I know the right side because delta h bar is given up there. So I have to just plug it in. So I get this plus this minus this minus half eta mu nu, and now this is the variation of the trace. Okay, and the variation of the trace is of course the trace of the variation, which is the trace of that whole thing, which is minus the divergence, minus twice the divergence of psi. Is that clear? These three terms are the variation of this, and this term is the variation of eta alpha beta delta h bar alpha beta by just taking the trace of that equation. I'll get del of psi here, and minus 4 times the same thing from the last term. Most people are nodding. The ones who are not nodding are the ones who have not done any calculation from the first day of this course with indices. The more you get familiar with indices, the more they'll be your friends. So please do it. Now you notice, I hope, that the last two terms cancel out. This term cancels with this term. So we get this. So this seems much better. There's a very good reason why this transformation should be familiar to us. Okay, is it familiar to us?
Small change from a flat metric.
What is it? Yeah, very good. It's the change from a flat metric under an infinitesimal change of coordinates. But this is extremely striking, almost shocking, because the metric, this is suggesting that this has something to do with the metric, but the metric is no longer a metric on space, it's a metric on space-time. Okay? And that, in a word, if you like, sums up the essence of general relativity. It's the theory of metrics on space-time, not on space. Okay? The fact that it's on space-time we could have guessed, because after all, special relativity told us that space is not just space, it's mixed with time and the whole thing should be called space-time. But the fact that a metric would arise from Newton's equation is new. Last time when I taught you something about a particle moving on a curved space, I didn't tell you where the curved space came from, which caused some of you to complain that you didn't know where it came from. In fact, it didn't come from anywhere. We just decided to study a particle on curved space for our own enjoyment. It was a free particle on curved space. But this time, it's not for our enjoyment. We want to study a particle in a gravitational field, and we have manipulated the gravitational field equations along with relativity and come to the conclusion that the true variable of gravity, which contains the Newtonian scalar potential as its 0,0 component, is something called h mu nu, and h mu nu behaves like a metric of space-time. Okay? So this is the reason why we need to study metrics on space-time and why we need to study curved space-time at all. It's a funny thing that in fundamental physics we never needed to study curved space, but we are obliged to study curved space-time because it's the root behind one of the fundamental forces of nature, namely gravity. Not only do we need to study curved space-time and metrics on such space-time, we also realize that the fundamental invariance of the theory that we are going to develop, analogous to gauge invariance in electrodynamics, is the transformation of coordinates. Here we have seen it at an infinitesimal level, okay, but that's a limitation of our study. In fact, it will turn out that all changes of coordinates behave like symmetries of this theory in the same way that gauge invariance behaves like a symmetry of electrodynamics. Okay? So we see more and more parallels between electrodynamics and gravity, except that in electrodynamics the field is a 4-vector potential, but the particles propagate in ordinary space-time. In gravity, the field is itself the metric of space-time, so space-time itself changes when we have gravitational fields. This is the revolutionary new idea. Good. Now there's one slide, so this leads us to the basic concept, if you like. Of relativity. Space-time.
Define h bar mu nu is, so you've made a change of coordinate, you've defined h mu nu to be h bar mu nu minus half eta mu nu, whatever. So you can actually write your equation in the language of not h bar mu nu and h mu nu, so you'll actually get delta h mu nu from the first step itself and not
From the first step.
No, I'm trying to say that instead of writing it as h bar mu nu, delta h bar mu nu, you've actually made a change of coordinates. When you've defined h mu nu as
No,
h.
I haven't made a change of coordinates.
No, I mean, what is
I made a change of variable. It's a different thing. I have not made a change of coordinates.
Sorry.
I made a change of the basic field variable.
Field variable. So you can do that initially and then get away to the result delta H mu.
See, H bar is the guy whose 0, 0 component is rho and whose other components were 0. We'll see that. Actually, I think we'll return to your question. The difference between H and H bar, you'll see in about 5 minutes. Okay? If you are not convinced, you can ask me again. Just to say what I've done now, H bar was the thing that came out by generalizing rho. Okay, so H bar 0, 0 is rho, and H bar all other components in this static situation are 0. Okay, H has some slightly different properties, so we needed to find H bar first, and when we found H bar, we found a transformation law like this for it, which was not very transparent, because these two terms we can understand, but this last term is not very transparent. So by the change of variables, we just eliminated the last term, and then we were able to find that, remember that this is nothing but the equation for infinitesimal change of coordinates on a manifold, but with the manifold extended from space to space-time. So, space-time is a pseudo. This is an important thing. The pseudo is the fact that there is time in it. Riemannian manifold. And in keeping with the way I am doing things, we will in due course tell you what is a manifold in all very detail, but we are trying to build up to it slowly, and we are trying to do that using, as far as possible, only physical principles and no heavy duty mathematics. Okay? There isn't any heavy duty mathematics in this result, which arises purely by combining two well-known experimentally verified physical theories. So this is the answer, this is the conclusion. And there's lots we can do to make this conclusion more solid and to then find the correct and final form of the equation, which we found in some simplified form as the equation for H. I think it's vanished, it was probably here somewhere. Okay. One important thing to realize is, one minute, let me finish, is that the equations we've been working on are linear. These are linear equations for phi. Therefore, they are linear equations for H bar and they are linear equations for H. It will turn out that the true theory is non-linear and we are only working in the linear approximation. That's an important one. Yes?
Sir, please explain the pseudo-Riemannian.
Pseudo just means that the metric has a signature minus one signature is minus. You are familiar with this fact. Okay? Even in special relativity, it's understood that while space is a flat manifold, Euclidean space, but the space that arises in special relativity is Minkowski space. That's not a flat Riemannian manifold, but a flat pseudo-Riemannian manifold, because out of 4 directions in that space, one has got negative signature. Negative signature is not not just a simple change. Of course, it has many important consequences. One of them is that in a real Riemannian manifold, distances between 2 points are always positive, and if the distance is 0, then the 2 points have to be the same. Here, distances between 2 points can be positive, negative, or 0. In one case we call it space-like, in another we call it time-like, in third case we call it null. And if 2 points are null separated, they don't have to be the same point. Okay? So this, on the one hand, is a bit of a headache from the mathematical point of view, because mathematicians have understood Riemannian manifolds and Riemannian metrics, but now we have to do something a little bit different. On the other hand, from the physics point of view, this is absolutely essential, because after all, time and space have to come with opposite signature. Otherwise, it can't be that I move so much in space and I move so much in time simultaneously, that these two things happen together. The fact that time and space have different physical meanings for us, that is a fact, and it doesn't go away just because we have something called Lorentz transformations. So the pseudo-Riemannian nature is very, very crucial. Okay. Nevertheless, whatever we can borrow from mathematics will have to do with Riemannian manifolds, and so sometime next week or week after, you will get some lectures on Riemannian manifolds, and then as physicists we will make use of that, modifying a few things here and there to suit this problem. Yeah. Okay, are there any questions up to this point?
So,
Yes.
so the way we work with Newtonian gravity, we look at gravity as a force that acts on particles and influences the motion.
Yes.
In the discussion that we've carried out so far, have we given up that idea yet?
Not yet, but we will soon. We will as soon as we start talking about freely falling lifts and accelerated frames of reference and the principle of equivalence, which I may start talking about later today or more likely next time. In a sense, although I've used physics theories, I haven't really gone into the physics of this fact, nor fully into the mathematics. I just wanted to point out to you that this fact follows from these manipulations that are guided by physics. Okay? Once we realize the fact, it's up to us to develop it and make a full theory out of it and understand its physical interpretation. So, both physical interpretation and mathematics of this theory will turn out to be difficult and we'll need to do it. Okay. Good. Now, let me first give you a test of this whole picture that should convince you that we are not somehow going down a wrong track. To some extent, this test will be nothing but running this derivation backwards, but there will be a new feature about manifolds. We'll bring in a new feature, which is a feature that's already familiar to you from my last two lectures. It will be new in the context of pseudo-Riemannian manifolds. So here's the question: if Newtonian gravity is really, as I'm claiming, an approximation to curved pseudo-Riemannian spacetime, then how does spacetime give rise in some intuitive way to Newton's equation? In other words, what is the equation in space-time language which reduces to Newton's equation? By Newton's equation I mean this, the fact that the acceleration of a particle is given by the gravitational force obtained as the gradient of the gravitational potential. Where does this come from? In language that originates with space-time. And the answer is very beautiful and very simple. The answer is, this is the geodesic equation for a particle in a particular space-time. But with some approximation. The approximation will basically be that the field is weak and we will neglect some higher order terms. Okay? So, you already saw last time what's a geodesic equation. It's a particular equation which you can get from a spatial metric, which tells you that a particle follows some trajectory that minimizes distance along that space. And here what it's going to do, it's going to extremize the Lorentzian distance, minus dt squared plus dx squared plus dy squared plus dz squared. This thing will be extremized by a particle moving in a general curved space-time. Okay, that we can expect. The interesting thing is that there is a particular metric whose geodesic equation reduces to that. If I can show you that, then you can really be convinced that what we knew all along for several centuries as Newton's laws are just an approximation to some much more impressive, much more beautiful and much more complex scale. So for that, let me tell you the space-time metric. Now, there are two ways to present a metric. One way is just to write it. After all, the metric is a 4x4 matrix, so I can write down the matrix for you. Okay. So I'm going to write down the matrix minus of 1 plus 2 pi, 1 minus 2 pi, 1 minus 2 pi, 1 minus 2 pi diagonal, and all other entries are 0. And I'm going to allow phi to depend on space. So it's a very particular metric.
Is this back calculation?
Yeah, sort of.
It seems like it's coming from thin air.
Oh, and then I can show you where it comes from. I think you asked me the question about h and h bar already, right? It comes from that. Very good. So let's justify. First of all, G mu nu, if we are going to consider a metric that represents a weak gravitational field, which could be well approximated by Newton's laws, then it should start with eta mu nu plus something. Do you agree with that? Because eta mu nu will be the case where it's flat and where special relativity applies and there's no gravitation, there's no force of gravitation. So you notice here that minus 1, 1, 1, 1 is part of this metric. Okay. To it, I should add h mu nu because h mu nu is the variable that transforms nicely under infinitesimal general coordinate transformations. Okay. Now I can calculate h mu nu for my system because of the following. Recall that h00 bar was minus 4 pi. Do you remember this? Okay. Now, what is the trace? H bar mu nu eta mu nu. This is equal to all other components of h bar was 0. So what's the trace equal to?
Minus 4.
I get plus 4 pi. You get minus?
No.
Good. So the trace is plus 4 pi. So now what is h mu nu? So h00 is h00 bar minus a half eta 00 times the trace of h bar, which is 4 pi. Eta 00 is minus 1. Okay, and this is minus 4 pi and this is plus 2 pi, so it's minus 2 pi. That's h00. What about hij? Well, let's do the diagonal ones. Hii. Okay. This means the two i's are equal but they are not summed over. Okay, they just take the value 1, 2 and 3. So it's h bar I minus a half, eta I is 1, and then the trace 4 pi. Now h bar I was 0. So this comes to minus 2 pi. So, and hij, you can easily see that all the other components which I haven't written are all vanishing. h0i as well as hij. So that means the entire matrix H is my diagonal minus 2 pi, minus 2 pi, minus 2 pi, minus 2 pi. Exactly what I put there. So it doesn't come out of thin air. I've derived this H from H bar and I derived H bar from pi. So it's completely consistent. Okay? So this is the metric I want to study. Just for you to get used to different ways of writing things, another way to specify the metric is to write it as, in terms of the line element, the Minkowskian or the pseudo-Riemannian line element, ds squared is minus 1 plus 2 pi dt squared plus 1 minus 2 pi dx1 squared plus dx2 squared plus dx. Is it clear that this is the same as writing it as a 4x4 matrix? I've simply written the right side is simply g mu nu dx mu dx nu. So what I did was to take all the components of g mu nu and multiply them by dx mu. That defines the distance in any manifold. Where there is an infinitesimal coordinate distance dx mu, then the distance is defined by this function of the metric. That's what the metric means. And in our case, the metric only had a 0, 0 and I component. That's why here you only see a dt squared and dx1 squared, dx2 squared and dx3 squared. But if the metric had a 0 I component, you would have had a term like dt dx or dt dy and so on. Or dx1, dx2 cross terms. Those are not there because of the special metric we've chosen. Okay? So in relativity, people often write the metric in this way, but you can as well write it as a matrix. I suspect finally that in word processing programs, it's much easier to write an equation this way than to format a 4x4 matrix. That's the main reason. Okay? Good. Now we have a metric. We want to calculate the geodesic equation. And the geodesic equation is pretty much the same as the one that you already learned how to derive for a conventional Riemannian manifold. It's just formally the same equation. It is x double dot mu plus gamma mu lambda x dot mu x dot lambda equals 0. Okay? That's why I was urging you for the last 2 lectures to work out this equation as the equation of a non-relativistic particle in a curved space. Once you got it in any kind of space, its continuation to pseudo-Riemannian is not a big deal. Just instead of ijk indices, you have mu lambda indices. Mu lambda, I remind you, these are all indices which take the values 0, 1, 2, 3. Ijk will always take the values only 1, 2, 3 space values. Okay? So that's the equation. So what remains to be done? Do you have all the data you need to write out the geodesic equation?
So the differentiation here is with respect to the proper time.
Yeah, very good. Thank you. So one question is, what is this dot? For a non-relativistic particle, dot was just time. Here, there is no just time. In fact, it turns out, it's a very nice fact about special relativity that you should know, but again, you might not have been told, that it doesn't matter. It can be, it's any parameter. So the dot is with respect to some parameter along the whole line. So it's called proper time sometimes. We'll just call it tau. And it really won't matter what tau is. We'll be free to choose tau as we.
The parameter is to be Lorentz invariant.
The parameter is treated as Lorentz invariant, that's correct. But after we solve the equations of motion, of course, they will equate some of these coordinates. They will give us some relations between the coordinates and tau. So those individual relations will not be Lorentz invariant because we are working in a particular method. So let's see the equations. First, let's look at this. So this equation has only one free component, mu. The others are summed over. So in particular, there are 4 equations. 4 geodesic equations in 4-dimensional space-time. Okay. However, we are trying to get 3 equations for the 3 space coordinates. So there must be some equation that's a little bit trivial. So let's look at the 0 component. X double dot 0 plus gamma 0 mu lambda x dot mu x dot lambda equals 0. I'm doing this slowly because you have to get into the swing of how to evaluate all the components of these equations, and it may not be something you've done already. So this part has the following parts: gamma 0, 0, 0, x dot 0, x dot 0, plus gamma 0, 0, I, x dot 0, x dot I, plus, now there will be another term when this is I and this is 0, but it will be the same because gamma is symmetric, because anyway this symmetrizes it, plus gamma 0 I j, x dot I, x dot j. So we have to evaluate all this. So we have to evaluate all these components of gamma. Now do we remember the definition of gamma? Gamma mu lambda is a half G mu alpha where the derivative is with respect to the four-dimensional space-time coordinate x lambda or x mu or x alpha. Okay? And this is the inverse metric. So we first of all need the inverse of this metric. That's very easy because we are working only to first order in phi. To first order in phi, if I just shift phi to minus phi, I'll get the inverse. Because if I multiply those two, then I'll get terms only of order phi square, which I am neglecting. Is that clear? So inverse metric is easy. But the important thing now is let's look at the zero case and then we'll see what's happening. Let's look at 0, 0, 0. So this has to be half G0. Now there's an index alpha which is being summed. So it can take the value 0 or I. Which value should it be? Only 0 because this metric is diagonal. The inverse metric is also diagonal. So this better be 0. Now I have here 0 nu comma lambda plus G0 lambda comma nu minus G mu lambda comma 0. What can you say about this term? It vanishes because there is no G0 nu. It's sorry. So, okay, we should be a little careful. Something is wrong. I have done something wrong here. It should have been 1 earlier. I am doing the special case 0, 0, 0. So these are all 0.
In the next example.
Oh, sorry, not in this step. Yeah, quite. Oh. Okay, in this step, it's all zeros, like this. So, okay, these two terms right away cancel, but this term, what can we say about it? It's also 0 because there is no time derivative because we are assuming that phi depends only on space. Okay, so this is 0. Now if you continue like this, you will find that this is also 0 and this is also 0. Okay, in all cases, there will be either a 0 component, a 0I component of the metric, or there will be a derivative in 0, and both of them are vanishing in the special metric we are working with. Therefore, at the end we learn that x double dot 0 is equal to 0. And this gives us a nice opportunity to, so it's a trivial equation. Okay, it says that as far as this time coordinate, it doesn't do anything special. In fact, x0 therefore is equal to a plus b tau, simply linear in tau. Okay, by shifting and scaling x0, we can simply remove a as well as b. So we can actually make x0 equals tau. It is not so strange. We've simply gone to a frame in which the proper time along the world line of the particle is the time coordinate of the particle. You can do that, but since this is special relativity, you don't have to do that, but you can do that. So we've just done it. So that's clear that this equation has done nothing more than identify x0 with tau, but that still leaves three equations, and those three equations are x double dot I plus gamma I j k x dot j, sorry, and I nu lambda Okay, so let me write out all the terms explicitly. Here there is a 0, 0 plus twice plus okay, so this is the equation we need to work out. Okay, so the first thing we can say about this is that this term is 0. Gamma I 0j is very easy to establish by a method similar to what I used, that for this metric that's 0. Okay, this is not 0 in general and this is not 0 in general. This one will actually be calculating and this one also turns out to be non-zero. However, I am going to neglect this term and show later that it's higher order in phi. This is a self-consistent approximation. I'm treating phi as something small. Okay, if phi is small, first I'll assume this is not there and I'll find out what this equation is. That equation will tell me how x scales relative to phi. This will depend on phi. And then I'll put that scaling back in this and show that it's a higher order contribution, which I'm allowed to neglect since I'm doing a linearized approximation. So with all that, the work really boils down to only the first two terms. So with one little assumption which I'll justify later, the equation has come down to x double dot I plus gamma I 0, 0 and then x dot 0 are both 1 because of this choice. Okay, so that's the equation. Okay, so it only remains to calculate gamma I 0, 0 and gamma I 0, 0 is a half Gi, so the second index has to be I, Gi 0, 0 plus Gi 0, 0 minus G 0, 0 I. And now you see we have some non-vanishing contribution. Of course this is vanishing because of diagonal nature of the metric, so is this, but this is not vanishing. Okay, so in fact it is half. What is G upper I? It's the inverse of 1 plus 2 phi with a minus sign. So it is times minus of 1 minus 2 phi. Okay. And then we have another minus sign, that's this one. And then we have G0, 0, comma I, which is minus 2 del I phi. Okay. Now, sorry, G upper I doesn't have this minus sign. This is plus because it's, in fact, it's 1 plus 2. Sorry. Actually, it won't matter, but it doesn't have a sign up. Okay. What should we do about this phi? Ignore because there is already a phi. Okay. So the approximation where phi is small is like scaling. Imagine that we scale phi, then we drop all terms with scale like phi squared or higher. So that means we drop this, collect all the signs, and we just get plus del I phi. So the equation has come out to be x double dot I plus del I phi equals 0, and that's good old Newton's equation. Okay. So we've actually shown that the geodesic equation for a particle in space-time with that metric, which are partly rubbed out, is Newton's equation. So it's now becoming more and more plausible that space-time being curved can be the origin of gravitation, and whatever Newton taught us is part of that as an approximation for particular kinds of metrics, but Newton didn't have access to those metrics which differ very radically from this one. Okay? The kind of systems that he was considering, which are basically heavenly bodies in slow movement, all have metrics approximately that, and therefore all have equations approximately like this, where phi remains to calculate for the Earth or the Sun and the Moon together or whatever you like. It just becomes a matter of tedious calculation, summing up the phi contributions from various heavenly bodies and solving this, or solving coupled equations where phi of the Sun, Moon and Earth all influence each other, each one moves in the field of the other, can be 2-body, 3-body, n-body problem, all that. But finally, it boils down to the fact that the metrics that Newton was considering, he was using this language for really of that time. It's very similar to imagining that people were doing experiments in electrostatics but they had never discovered magnetism. Okay? Historically, that's not what happened. Magnetism was discovered experimentally. It's very accessible force. It's even the Earth has a its own magnetic field. So magnetism was known. But theoretically, you could imagine that somebody had only electrostatics and no magnetism. In that case, they were working with 4 vector potentials which had only the scalar potential part turned on and the rest was 0. Okay? So, unknown to him, Newton was working with metrics which had only these diagonal components turned on, and that too in this proportion, because then they make the variable h bar to have only a 0, 0 component. And then Newton's equation was right. Moreover, if the fields were not very large, not very strong, so the neglecting nonlinear terms like this, or using that inverse of G just involves a simple change of sign of phi, those things are all justified only for weak fields. Yes?
So here now it is.
Yeah.
So here shouldn't we write, I mean, contravariant added to contravariant and covariant added to covariant? I mean, in this sense,
Yeah.
I mean, now this del I should be a superscript I,
Yeah.
and then after that it should.
What's the difference between a superscript I and a subscript I?
Superscript I is the contravariant.
Yeah, but what's the difference numerically?
I mean, in case of this convention, it doesn't have any difference.
The reason is that we are working in a flat, we are working in weak field, so the metric in which this is all happening is approximately flat. For a flat metric, I gets raised and lowered by delta ij, so it's the same thing whether it's raised or lowered. So we can do it. We should be careful about our conventions where it's required, but here it's not required. Okay. So this is basically the point I wanted to make today, and I hope this will motivate you to believe that Newton's theory should be superseded and replaced by a new and more complex theory of general relativity, in which space-time is described, in which gravitation is described by the metric of space-time. And it's nice, this example of course is a favorite thing because it shows you very clearly that the familiar gravitational laws are part of the story. But clearly they are not the whole story, because A, nobody said that the metric had to have only diagonal components. B, nobody said that those components had to be small. Okay, once we accept that space-time can have a non-trivial metric, then it can be any non-trivial metric. We have to find a principle which tells us what metrics are allowed or not. Okay. So we have to worry about that, and we'll start doing that from next time. One small loose end I should tie up. I didn't show you that this term is negligible, but from this equation, you can see the following, that if I scale phi by a number lambda and scale x, so if I scale phi by lambda squared and x by lambda x, then the equation is unchanged. I don't do anything to time. I scale x by a factor lambda, so this becomes lambda times x. Phi by lambda squared, but d by dx gives me 1 lambda in the denominator, so both terms scale by lambda, so lambda drops out and the equation is unchanged. Okay, so lambda is the parameter which I imagine that I am taking it arbitrarily small, like an epsilon, so I will neglect terms of higher order in lambda compared to this term which scales like lambda. Equation unchanged and scales, the whole equation scales like lambda. Now I am adding to it this term, and I should find out how it scales. Well, without any work, I can guess that these gamma, ijk, whatever they are they depend on first derivatives of phi. There's nothing else they can possibly depend on. Okay? So these terms are of the form phi first derivative with respect to something and then x dot, x dot. So if I scale like this gets a lambda, this gets a lambda, this gets lambda squared and divide by lambda, so lambda. So the whole thing is of order lambda cubed. So it's small compared with the original equation, and that's why I could draw it. Okay. This also tells you one more thing, which is that if this is true, if this is the true theory and not Newton's theory, then there must be some experiment in which I can detect the fact that I dropped some term of order lambda cube, because after all lambda is some typical size of that Newtonian potential, which is small but it's not zero. Okay? It means that Newton's equation is wrong, it's only an approximate equation. The correct equation is this geodesic equation, the full one. And I'm not allowed to drop any terms. I can approximately drop them, but as an exact equation I'm not supposed to drop things. So whatever I've dropped, there is a price. Somebody will come along with a very, very high precision experiment and find those terms. Okay? Then finding those terms will distinguish in a decisive way between general relativity, which gives those terms, and Newton's equation, which doesn't have those terms. Okay? Is that clear? So therefore, it's completely experimentally testable which of these things is right. Of course, if experiments had said that this is right with no correction, we'd have been in a lot of trouble, because we would have never found any relativistic version of Newton's law of gravitation, and we would have two theories that don't fit with each other. But experiments sided with the view that spacetime is a manifold. Of course, you know Einstein's famous statement when he was asked what he would do if experiment didn't support general relativity. He said the equations are, then I would feel sorry for nature, the equations are right. And it turned out he didn't have to feel sorry for nature, the equations are in fact right. So, okay. So this, I think this, although it's taken 2.5 lectures to do, but I think this should be the kind of comprehensive motivation for the course. And from next time we'll start talking about inertial and non-inertial frames, principle of equivalence, and so on. And we'll see that that's another way which will finally lead us to space-time geometry. And then it will allow us to write down some equations. Yeah, any questions? Yes.
So if tau is not a prime parameter, and tau is not a proper time, then geodesic equation will have a right hand side. And you have to prove that in this case right hand side is second order in order to do it. Since you have taken x0 is equal to tau, tau is not an affine parameter.
No, but that's part of the solution. The equation, I started with the equation in which tau is an affine parameter.
Without the geodesic equation, if tau is not a affine parameter, will have a right hand side.
No, look. The geodesic tau is an affine parameter. I have not chosen tau in any way. I have not chosen tau not to be an affine parameter. This is a solution for x0 in terms of tau. I have not done anything to tau. Tau remains the affine parameter. I have solved for one of the four coordinates of the particle in terms of tau. It's a solution of the equation. I am not changing the equation. I am finding a solution. I have done nothing to tau.
But you can take time to be tau only if the spatial components of velocity is present. But in this case, spatial components of velocities are not zero each other.
Yeah.
So tau cannot be.
Actually, yeah, sorry. So I think what you're saying might be related to the following thing. I was a bit hasty in arguing that this term drops out, but actually I think it does drop out. This is the point. These are the terms you are worried about, but they drop out because gamma 0 ij is 0. Again, it's not a general space-time, it's only this space-time. This space-time is very special. First of all, it depends, it's only diagonal. Secondly, it depends on only one function. Thirdly, that function depends only on space and not on time. With all those things, this gamma 0 ij, as far as I can think standing here, is 0. If it is not 0, then we would have to resort to again the statement that it's quadratic in velocities and hopefully small. But I think it's actually 0. You can convince yourself of that, because I'll have to have a G00 upstairs. That means downstairs I either have Gij comma 0 or G0I comma j. Both are 0. So gamma 0 ij is just 0. Okay, so then it is good. Okay. Any other questions? Yes.
Don't we need to assume that particle velocity is non-relativistic?
Yeah.
To be able to neglect the last one?
Yeah, I mean that's this, is it? That's exactly this argument. Because you see, the fact that phi is small tells me that the acceleration is small. Okay? I'm scaling, okay, I mean if you like you can assume that, but that's implicit in this calculation. I'm assuming that I'm in a system where a particle, okay, I don't give it a large initial velocity, it moves under the influence of a weak gravitational field. So it's not going to, for a short amount of time, it's not going to become relativistic. But if you want, I can add that assumption, because anyway this is expected to happen only under that assumption. Okay, so then if there are no more questions, so we will conclude.